Hi guys, Dr. Kruse here. Elementary statistics. We're going to discuss the mean or the average of your sample and its standard deviation. We're going to calculate standard deviation by hand a couple different ways, and then I'll show you how to do it on the graphing calculator. First things first, let's learn some terminology. If you're talking about the sample, all right, I always describe sample as the ones I could catch. For example, if I wanted to measure something about all the Black Angus cows in the world, well, that would be my population average, and my population standard deviation. But I can't catch all the Black Angus cows in the world and measure their average weight or average height or whatever I want to measure. So the ones I can catch are, the ones out in the pasture. If there's 30 or 50 or 100 out in the pasture, I can catch those 30 or 50 or 100, and that's my sample. And I can find an average, mean means average, I can find an average weight of the sample, an average weight of those 30 Black Angus or whatever. And I'll show you how to calculate the standard deviation, which lots of times I'll call that the give or take. I'll say the average of my sample is, maybe 1,000 pounds if I'm measuring average weight. And then this will be standard deviation. I'll say give or take 100 pounds either way. So the average weight of my Black Angus cows that I could catch is 1,000 pounds, give or take 100 pounds either way. So it could be as low as 900 pounds, could be as high as 1,100 pounds. So think of standard deviation as kind of a give or take. Symbols for your sample average, your sample mean is x bar, just a lowercase x with a bar over it. We say it just like that. Your sample standard deviation is a lower s for standard deviation, and we just say s. If you're talking about population, like you're talking about all the Black Angus cows in the world or whatever, the average of that is called mu. Kind of looks like a U with a tail down the left here. Mu. It's spelled MU, but it sounds like this. It sounds like mu. The population standard deviation is a lowercase sigma, which is just an O with a little curly Q up top there. And that's a lowercase sigma. So keep those straight. For the sample, it's x bar and s. For the population, it's mu and sigma. All right? Okay, standard deviation, that give or take, above or below the mean, it's just your average distance from the mean. So all of those cows that I caught, on average, how far are they away from the average? Okay, mean means average. So not every cow is going to weigh exactly 1,000 pounds. They're going to be a little bit away from that, a distance away. They're going to be a little bit lighter or a little bit heavier. So each one of those cows, I'm going to see how far from the mean they are, what their distance from the mean is, and then I'm going to average all those distances. All right? Everybody's going to vary a little bit. All right? Everybody's going to vary from the mean a little bit. They'll be a little heavier or a little lighter. And I'm going to average all those variances. I'm going to average all those deviations. Everybody's going to deviate from average a little bit. They'll deviate a little bit higher or they'll deviate a little bit lower. And I'm going to average those deviations. Okay? Now I'll show you later that we have to square that average of those deviations. All right? We have to square the deviations and then average those. We'll see this in just a minute when we calculate this by hand. But when I average all of those deviations, which I have to square, that's called the variance. Excuse me, got choked up. That's called the variance. And our last step in finding standard deviation is to square root those squared deviations, that average of the squared deviations. Our last step is to square root. Sounds confusing right now, but it's not too bad. But the average of the squared deviations is also called the variance. All right, so for example, let's say I give a test, all right, and I have like 30 kids in the room, and they all take the test, and I add up all those test scores and divide by 30. So my average test score was, say, 75%. I would say the mean, or the mean of my sample is 75. In other words, x bar is 75. I'm talking about my sample, the 30 people in my classroom. I'm not talking about all of the statistics students in the whole world. That would be population. That would be mu if I was going to say it that way. But I'm just talking about the 30 students in my classroom. So I'm talking about a sample, the 30 I could catch. So the average of my sample, X bar, is 75%. Now what about my give or take? And maybe I'm talking to another professor and I say, oh, the average was about 75, give or take 10 points. So it could be as low as 65, could be as high as 85 if I go 10 points either way. And that's going to encompass most of the class. If I give myself a give or take of 10 points. Well, that give or take officially, we're going to call that the standard deviation. So if I say give or take 10 points, I'm saying the standard deviation of my sample is 10 points either way. Could be 10 points higher than 75, could be 10 points lower. And again, if you're talking about the population, if you're talking about all the students in the whole world, then you'd be talking about sigma. So it depends on what you're talking about. Usually we're talking about the sample. Usually we're talking about the sample. We're talking about the people we could catch, or the cows we could catch, or the fish we could catch. So, and the population number, we kind of estimate based on the measurements we make in our sample. So our sample average, our sample mean is 75, and our sample standard deviation is 10. Okay, here's kind of a picture of what that would look like. Here's your normal distribution curve. And in a normal distribution curve, right here in the middle, that's your average. That's your X bar. That's your sample mean, 75. And then, if there's 100 people in the room, or 100 students in the room, or 100 cows in the room, 100 cows in the field, I guess, there would be 50 to the left and 50 to the right. So this picture, this curve, kind of encompasses 100 people, 100% of your sample, of your population. They're all going to land in here somewhere. Now the tallest part of the curve here, this is where most of the people are. So most of the people are really close to 75 on this test. All right, now this is a little lower. 65 is a little lower, so fewer people scored 65 and fewer people scored around 85. Most of the people scored 75. That's the highest part of my curve. And then as we go out toward the edges of the curve, we have fewer and fewer and fewer people scoring that. So by the time I get out here to 95%, I didn't have very many of those people at all. I had a whole bunch of people score around 75. Not very many scored 95. And the same thing goes the other way. I had a whole bunch of people score 75, but by the time I get out here, that's not very high. I didn't have very many people score 55. And by the time I get out here to 1, 2, 3 steps above average, I have hardly anybody, maybe one person out of 100 out here. And out here past 2.5 steps, we call that an outlier. Outliers are surprises. They're unusual. They're things we didn't expect. So like maybe I thought my test was pretty hard and I didn't really expect anybody to make 100 on it. But maybe out here I had one person that aced it and got the extra credit bonus question, and maybe one person got 105%. Well, that's a surprise. That's unusual. We call that an outlier because it's lying out here to the right of 1, 2, 2.5 steps. Anything higher than that, so between 95 and 105, this would be about 100. Anything higher than 100, that's unusual. We call that an outlier. Same thing going the other way. 1 step, 2 steps, and 2.5 steps to the left. Anything lower than that, I would also be surprised about. This would also be unusual. All right, if somebody scored a 45 on my test when the average was 75, I would find that really unusual. But maybe one person scored a 40 or a 45 or a 46 in this area. Not very many, maybe 1 out of 100. Unusual. So our outliers lie 2.5 steps above the mean or 2.5 steps below the mean. Okay, and just to give you a, whoops, hang on, I got something going on here. There we go. Okay, my screen messed up. Okay, just to give you a picture of kind of what's going on here, most of your people will be within 1 standard deviation of the mean. This is X bar. Standard deviation stands for how wide this step is. Remember we said standard deviation was 10 points? We said the average was 75, give or take 10. So plus 10, plus 10, plus 10. That gives me 3 standard deviations to the right. And minus 10, minus 10, minus 10 gives me 3 standard deviations to the left. Now this covers almost everybody in the room. If there's 100 students taking the test, this should cover all 100. They should all be under here somewhere. Now most of them are right here. All right, this is the high point of the curve. Most of them are within 1 standard deviation of the mean. In fact, a good rule of thumb is that about 68% of the room will be between 65 and 85, between 1 standard deviation below and 1 standard deviation above. That's about 68 out of 100 people. So out of 100 people in the room, about 68 of them should be in this area. That's most of the room. Call it 2/3 or so. All right, now if I take another step, if I go 2 standard deviations to the right and 2 standard deviations to the left, well, that'd be from 55 to 95. That should cover about 95 out of the 100 people. That should cover 95% of the room. So 2 steps below average and 2 steps above average should cover 95 people. There's only 5 people left out of 100 that are maybe below 55 or above 95. We've covered 95 out of 100 people. There's only 5 people left. Now, if we take one more step, all right, 1, 2, 3 steps, that's 3 standard deviations to the right, and 1, 2, 3 standard deviations to the left, that's from 45 to 105. Well, that should cover virtually everybody, 99.7% of the room. That'd be 99.7 people out of 100, or it might make more sense if you say 997 people out of 1,000. So if there was 1,000 people in the room, they would all be under the curve within 3 steps except for 3 of those 1,000. All right, so 1, 2, 3 below average and 1, 2, 3 standard deviations above average. That's virtually everybody. There might be one guy out here really, really high, or there might be one guy out here really, really low, out past the 3rd standard deviation, but it's pretty rare. So that's why we draw the curve this way. If we go 3 standard deviations either way, we should get virtually all of the population, all right? We might miss one guy. 997 out of 1,000, we would miss 3 people out of 1,000. But if I'm talking percent, that's out of 100. So 99.7% are within 3 steps of the mean. That's virtually everybody. We just might accidentally have one person outside of -3, or we might have one person outside of +3 steps away from the mean. All right, let me walk you through calculating standard deviation by hand. I'm not a big fan, but it is kind of interesting to see, where it comes from. And then we'll probably just do it mostly on the calculator, is what I would advise. So maybe I just have this basketball team, and this is their height in inches. Now your raw data, these are the heights of the players. That's called X. Your raw data, we call those X values. So I have 5 values here. That's what the N equals 5 means. Number is 5. And I have 72 inches tall, that's 6 foot. All the way up to 78 inches, that's 6'6". So a fairly tall team, but nobody's really unusual. They're a little taller than average. But let's just look at these 5 members, and let's figure out what the average height of just these 5 guys are. Well, to find an average, you add it up and divide by how many there are. If we add it up, we get 375 inches. This is uppercase sigma. And uppercase sigma in math means summation. It means sum. It means add them all up. So this is saying add all the x's. The sum of all the x's is 375 inches. Now, since I want to average it, remember average of your sample is called x bar. This is a sample because this is not all the basketball players in the world. That would be the population. This is just the 5 I could catch and measure. So my sample average, x bar, my sample mean, is the total divided by how many there are. 75 inches is my average. All right, so we know this sample average is 75 inches. Okay, now what I'm looking for is called the deviation from the mean. Deviate means you stray from average. You're either above average or you're below average, but deviate means you stray from the average. Like this guy here, if the average is 75, this guy's a little bit shorter than 75. He's actually 3 inches shorter than average. How do we calculate it? We take his height minus the average. Turns out he's 3 inches shorter than average. That's the negative. So you take the x value, the measurement, minus the average, and turns out he's 3 inches shorter than average. This person here, 2 inches below average. This person here is a little bit tall. They're 1 inch above average. Same thing with this one, and this person here is 3 inches above average. So if I want a standard deviation, these are my 5 deviations. If I want a standard deviation, that's another way of saying I want to average these deviations. Well, to average these 5 deviations, I would add them up and divide by 5. But look what happens. When I add them up, they turn into 0. This is the sum of my calculations here. How far did everybody deviate or differentiate from the mean? The sum of my deviations adds up to 0. These negative 5s cancel out the positive 5, and it winds up being 0. And when I try to average that, I get 0. And that's just nothing that makes sense. That's not helpful. I can't say the average height of this team is 75 inches, give or take 0. That doesn't make sense, all right? Because that would mean that they're all 75 inches and there's no deviation. Well, there's obviously a deviation. I mean, actually, none of these guys is 75 inches. They're all above or below. So this is not a valid calculation because the negatives are messing up our average. When it adds up to 0, man, I can't get a decent average. So we're going to use a trick. I want to average these deviations, but it didn't work with the actual deviations. So I'm going to use a math trick, and I'm going to square each of the deviations just to make the negatives go away. So negative 3 times negative 3, when I square it, turns into positive 9. So note that it turned into positive, but also got a lot bigger. And we're going to have to reverse that here in a minute. So I'm making negative 2 into a positive 4. I made it a lot bigger. I made it positive and a lot bigger. So we're going to calculate the average with these large numbers, but our answer is going to be way too large, and we're going to have to bring it back down to life size here in a minute. So square each of these numbers. Now that I have 5 positive numbers, now I can calculate an average. So I'm going to add the squared deviations, all right? The deviations were over here. This is my deviation, negative 3, which I then squared. So I squared the deviation. I'm going to add them all up. That's 24. All right, and now I'm going to average it. So I want to take 24 and divide it by 5. But here's a little exception to the rule. The exception to the rule is when you're dealing with a sample, all right? This isn't all the basketball players in the world. It's just the 5 I could catch. So this is a sample. When you're dealing with a sample, and you're trying to average, you have to divide by 1 less than what you actually have. So instead of dividing by 5, I actually have to divide by 1 less than the number I have. I have to divide by 4. All right, it's an exception to the rule. So I'm going to take my squared deviations, I'm going to add them up, I'm going to divide by 4, and what I have is an average of 6. But I can't say that that's the standard deviation because all of these numbers were squared. That's actually the squared standard deviation. It's way too big. So to bring it back down to regular size, all right, I made these guys all too big. 3 turned into 9, it got bigger. 2 turned into 4, it got bigger. So to bring these back down, I have to unsquare it. And unsquaring it, mathematically, that's called the square root, if I want to undo this squaring. So if s squared equals 6, this is way too big. It's the squared standard deviation. If s squared is 6, then I need to square root it to get rid of that square, to undo it, which takes us down to the actual standard deviation of 2.45 inches. All right, it's a little hard to understand the first time around, but I want to find the deviations. I want to average them, but it didn't work. So I use a trick and I square them and I average those instead. All right, the answer I get is an average deviation, but it's an average of the deviations that were too big. It was an average of the squared deviations. So my final step is to unsquare this, square root it, and I have my actual standard deviation. Down here's a shorter method using a formula. All right, this says, well, you can find your s squared. Remember, that's the number that was too big. You can find your s squared if you add up all the x squareds minus the sum of your x's, which you then square, divided by n, and all of that's over n minus 1. Well, let's walk through that. This is just a little quicker way of doing it by hand. So if I add up my x's, it's 375. We already knew that. That's the sum of the x's. Now, if I square each one, all right, I'm squaring each one, and I add those up, that's the sum of my squared x's, this 28,149. Now I just plug them in over here where they go. I need the sum of the x squareds. That's my big number, 28,149. Minus, in parentheses, I need the sum of the x's. That's my 375, which I then square and divide by 5. Over, here's my adjustment. Since it's a sample, I have to divide by 1 less than what you have. So I'm going to end up dividing by 4. Remember, this number is too big. It's 6. So your final step is to unsquare it and end up at 2.45 inches. All right, I'm going to show you the third method, which is simply using the graphing calculator. So let's find the mean and standard deviation using the TI graphing calculator. And we're going to practice with the same data. This is the same basketball team, same 5 guys. The average is still 75. Standard deviation is 2.45. So we calculated the standard deviation 2 different ways by hand. And here's how you do it on the graphing calculator. All right, I'm going to work it on the TI-83, but the TI-84 is virtually the same. So I'm going to start with my statistics button right here. Statistics, all right. And I want to edit the table. That means I want to put my 5 basketball heights into the table. So I'm going to edit. Now I've already entered mine here. You just enter them in list 1, all right. We can enter another team in list 2 and another team in list 3 if we want to. But I just have one team, so I'm going to put them in list 1. All right, now I want to calculate, all right? So I start over. I hit Stat again, and I want to arrow to the right and go to Calculate. And I want that first option that says One Variable Statistics. Now it's waiting for me to tell it which list I want to work with. If I don't tell it anything, it's going to assume that I want list 1, which is what I want, but I want to show you down here. I'm just going to go ahead and put in list 1. Now it's above the 1 button. It's in yellow, so that's my second function of the 1 button. So I'm going to hit second function of the 1, which brings up list 1. But it's automatically going to go to list 1 if you don't tell it. All right, I'm just kind of over-explaining. And there it pops up, our statistics. Let me try and get it out of the light here. All right, so there's X bar. There's our 75 average. There's the sum of the x's and the sum of the x squareds that we used in that second method for calculating standard deviation. This is a uppercase S. It should be a lowercase s. That stands for our sample standard deviation of 2.45 when you round it. And this here is trying to guess at what the population standard deviation is, but we're going to ignore that because you can't really guess at it with only 5 values. Here at the bottom it says n equals 5. You had 5 values. And then if we go ahead and scroll down, there's some extra information here. At the bottom it says, hey, your shortest guy was 72. All right, that was this guy right here. Shortest guy is 72. It says the guy in the middle was 76. That's the median, the middle. And it says the tallest guy is 78. That's the max. And it also breaks it into quartiles, but that's another lesson. I do want to show you my oops message over here. If you're going into your table, get out of the light again, and maybe you want to clear your table, the slowest way and easiest way is just to hit the delete button right here. So I'm going to hit delete, 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 delete. That's kind of the slow way. But sometimes students get in a hurry and they actually go up here too high where the title of the table is, and they accidentally delete that. So you see my list 2 is gone. Well, that's a problem. You know, we might need that list. So don't panic. If you accidentally delete a list, just start back over at Stat and go to Setup Editor, and it'll set the table back up again. So Stat, I'm going to choose number 5 here, Setup Editor, and I'm going to hit Enter, and it says Done, and it put my table back to normal. So Stat, Edit, there's my table, and there's my list 2 that came back. So here's my oops instructions if you accidentally delete a list. Okay, and finally I want to show you just kind of how this maps out on a graph. So with our basketball team here, our average height was 75 inches. That goes in the middle of our graph here. The average, the one that was most common, was about 75 inches. All right, give or take a standard deviation of 2.45. That means if I go 1, 2, 3 steps to the right, 3 standard deviations to the right, I'm going to add 2.45, which gives me this height, 77.45 inches, and I add another 2.45 inches to get 79.9, and I add another 2.45 inches to get a final standard deviation of 82.35. So the mean, the average, plus 3 standard deviations takes us out to 82.35 inches tall. That's pretty darn tall. We're getting pretty close to 7 foot there. So 7-footers are basically outliers. But to map this out, we want to go 3 steps to the right and just throw it in reverse and do 3 steps to the left. So starting with your average, minus 2.45 gives us 72.55, minus 2.45 gives us 70.1, and minus another 2.45 gives us 67.65. So if you're 67 inches tall, relative to this team, you are basically a really, really short outlier. Anything past 1, 2.5 steps, this is kind of outlier range. And anything above 1, 2, 3 standard deviations, this is outlier range. Now I went ahead and put dots where the players land. So 72 is right about there. 73 is right about there. A 76-inch tall player, there were 2 of them, so I stacked them. And then the 78-inch tall player is right here. So kind of look at where the team landed with our standard deviations. Here's the middle. Here's X bar. Here's 1 standard deviation to the left, and here's 1 standard deviation to the right. Now inside of that is 3 of our 5 players. That's most of the team. And that's kind of how you want the graph to fall out. You want most of your data to land in here between 1 standard deviation left and 1 standard deviation right. This is about 2/3 of the people in the room, or 2/3 of the team. It's about 68%, all right, rule of thumb. We do have a guy who's a little taller than average, but he's still normal, all right? You don't hit abnormal until you're 1, 2.5 steps out. So anybody that's taller than this would be abnormal, would be unusual, would be an outlier. So this guy's, he's taller than average, but he's only 6'6", and there's a whole bunch of people that are 6'6", so he's not unusual yet, but he is taller than average, and he's outside of that 1 standard deviation. And this person here is a little shorter than average, but not much, all right? 72 inches, he's 6 foot tall. There's a bunch of 6 foot tall people, so not unusual at all. But for this team, 6 foot is a little bit shorter than average, but not unusual at all. Unusual would be 1, 2.5 steps out here. These people here would be unusual relative to this team. All right, and I do want to show you one last thing. It's coefficient of variation. Remember we said everybody varies from average a little bit. Now the larger this calculation is, CV, coefficient of variation, that just says the more spread out your data is away from the mean. All right, and after you do a couple, you'll see how the coefficients of variations change, but it's just a measure of how spread out your data is. So the coefficient of variation is simply the standard deviation compared to the average. All right, how wide are those steps that you're taking compared to your average? Now we just multiply by 100 because we want to write it as a percent, but just compare your standard deviation to your mean. All right, make that division, then times 100, and you'll come up with what's called the coefficient of variation, just a measure of how wide or how close together your data are away from the mean. All right, guys, and that's all I got for you for today.